So let's get started. I have a script here, but this belongs in the morning session, so let me see what's relevant here. We have placed as much power as we could afford. Please share the outlets. Outlets could be in your row or the row behind you or in the row in front of you. There's apparently a survey for the tutorial, but I don't know if this is the correct URL. Anyway, apparently there's this guidebook mobile app that also has a link to the survey for the tutorial. And there's a time for the break, but that's the AM break. I don't know what time is the break in the afternoon. Sorry about that. But anyway, so let's get started. I'll try and figure out the time for the break and let you know eventually. 3? All right, awesome, Brian, thanks. So Brian, our AV master, is telling us that it's 3, the break. Awesome. So I split this presentation in 2 parts because it's really 2 different subjects, although in the end they converge. So this is Decorators and Descriptors decoded. The first part is Decorators decoded, and the second part is going to be about Descriptors. This is my attempt at doing a gentle introduction to metaprogramming, which is never a gentle subject, but I try. Anyway, so that's me. Right now I'm working for ThoughtWorks. ThoughtWorks is a software development consulting company, a software engineering consulting company, an American company that has offices in 15 countries, and I work in their São Paulo office. And the main claim to fame of ThoughtWorks is that ThoughtWorks was one of the pioneering consulting companies to use the agile methods. In fact, out of the about 15 people who signed the Agile Manifesto, 2 of them are still with ThoughtWorks. One of them is Martin Fowler, author of some famous books. He is our chief scientist, and the other is Jim Hinesmith, who is a director in ThoughtWorks in the US. So those were 2 guys who were there at that meeting when the Agile Manifesto came up. And also other movements that are strongly identified with ThoughtWorks. More recently, the continuous integration and the continuous delivery practices and DevOps. All of these things are things where ThoughtWorks has had a pioneering role. So I'm very proud to be working there. And but you probably know me because of my book, right? Who knows about my book? Awesome. And who actually has my book? Awesome. Thank you, guys. Anyway, so this book was released in 2015, a few months before I joined ThoughtWorks, and it has now been translated into several languages, including 2 versions in Chinese. That one was the first one. The Go Top edition is a traditional Chinese, was released in Taiwan. And just last week I learned that there's a simplified Chinese edition for mainland China. So I'm very happy about that. And it's also fun to see the book. I wrote the book in English. It was translated to Portuguese. I revised that edition, but I couldn't revise the others because I don't know the other languages. But it's interesting to see how the book is named in some languages. For instance, the Russian version, a Russian guy translated it as Python to the heights of excellence. Isn't that awesome? Yeah. And the Chinese means smooth Python, which is also fun. Anyway, so this book grew out of a lot of classes that I used to teach about Python, both in company and online. And a lot of the content, most of the content you're going to see is in the book as well, although I did develop a couple of different examples to demonstrate stuff. So what we are going to cover on this first part is the idea of functions as objects. Then we're going to introduce decorators, looking first at registration decorators, which is the simplest kind of decorator that you can write, and that don't require that you understand what a closure is in order to understand how they work. And then we talk about closures and about decorators that affect behavior, parameterized decorators, and class-based decorators. This is where you will find the resources for what I'm going to present. So the slides you can see online on speakerdeck.com/Ramalho. So my last name you pronounce as if it started with an H, Ramalho. In Portuguese, that's how we pronounce the R in the beginning of a word. So that's where you can see the slides online, and there are other presentations of mine over there. And this is the repository of the GitHub organization for the Fluent Python book. And I created a repo there called Decorators, Descriptors. So if you just go to this first part, github.com/fluentpython, you will find this page, and there are two pinned repositories. One of them is the one that you want, this one, Decorators and Descriptors. This one has the example code from the book, and there are other repos over there. Okay, can I, does anybody still, is somebody still copying the URL? Yeah. All right, can I go? Okay, so let's talk about functions as objects. And I kind of say naturally here, because actually this is a pretty obvious concept unless you've spent too much time in Java. Because only in Java 8 functions became objects in Java. So it's crazy. You have this object-oriented language, and you have this very basic building block of programs that are functions or methods, but they were not objects in the Java language until Java 8 came around, right? And in fact, a few years ago, I saw a presentation. It was, I think it was in PyCon, and so this guy showed, this is the list of the 10 most popular programming languages that run on the Java VM. And among them, Java is the only one where functions are not first-class objects. So a few years ago. So really, it's an exceptional situation with Java. Although earlier in the history of programming languages, it was common for languages not to implement functions as objects, particularly when they were not object-oriented languages. So, for instance, in C, a function is not an object. In Pascal, they're not objects, so on. Anyway, but Guido says, and I quoted this, that he has never really considered Python to be heavily influenced by functional languages. So I'm not going to paraphrase. I'm just going to give my interpretation. So my interpretation of this is, Guido had this influence coming from other languages like C and Algol. But he decided to make Python object-oriented, and in that context, it was kind of obvious to think that how do you look at functions as objects? What does that mean? If a function is an object, what does that mean? Right. So, and that's the approach he took. But it's not really. Python is not a functional language in Guido's opinion, and so. What it means to have a function as an object, and this is the way people say functions are first-class objects. Guido in that quote also said that. So here's a question, just so that we can think about this concept. Are there, in Python, second-class functions? Or are all functions in Python first-class objects? What do you think? Yes. Yeah, that's a very interesting point. Yeah, so lambdas are kind of second class in a way, but they are still objects. What you create with a lambda is something that is an object that you can, so it's something that you can create at runtime, you can assign to a variable, you can pass as an argument to a function. That's the main use case actually for lambdas, right? And you can return a lambda as the result of a function. So in that sense, lambdas are as much first-class objects as functions are. The limitation with lambdas is more syntactic, right? The fact that you can't use statements in a lambda means that you can't use if, you can't use while, so it becomes limited from the syntax point of view. But what you create with a lambda is as much a function as what you create with the def statement. So really, there are no second-class functions in Python, and in fact, most languages that I know about that have first-class functions don't have second-class functions. The idea when you say first-class function is really you're shortening this more precise term, which is functions as first-class objects. It doesn't mean there are second-class functions. It means that functions in the language are considered first-class objects, and that means all of those things. So a good example of passing a function as an argument is this. So you have this list of fruit, and I am sorting it, and I pass the len built-in function as the key argument to the sorted function. And then what it does is it returns it creates a new list, iterating over this object and sorting the elements by the result of applying that function to each of the elements, right? So you have the list of fruits ordered by the len of the word. Does that make sense? I think this is really elegant. And it's a good example of passing a function as an argument to another function, right? So because functions are objects, and this I'm using a Jupyter notebook. Who has used Jupyter notebooks before? Awesome, yeah. I sometimes use them even when I'm not doing analytics, because they're just good to demonstrate stuff. And so here I create this Fibonacci function, and I exercise it here. And so there are some magic commands in Jupyter. One of them is the question mark. So if I put question mark in front of the name of something, it will tell me stuff about that something. So in this case, it's giving me the signature, which notice I'm using the new annotations syntax in Python just to enrich this signature. So I can see it here. I can see the doc string, which is this. Yeah, and the type. Anyway, so this shows that Jupyter is handling the Fibonacci function as an object. So it's looking into it, extracting attributes such as the doc string and the signature and so on, right? On a lower level, if you look at Fibonacci, you will see that it has several attributes. If you do dir Fibonacci, you will see attributes such as the dunder doc. And here I'm using this convention of calling, whenever we see this syntax of 2 underscores around a name, we call this a dunder name. So the dunder doc, dunder annotations is a shortcut. Anyway, so dunder doc is an attribute that has the doc string of the function. Annotations is another attribute that contains a dictionary with the names of the annotated parameters, and the special name return gives the name of the return type, or the return annotation, to be more precise, because Python is completely agnostic about the meaning of those annotations, right? They don't need to be types. They can be whatever. Anyway, but they are usually used to denote type. Anyway, and here's an interesting thing. A function has a code attribute, and the code attribute is something that has other attributes, such as var names, CO var names. And CO var names is a tuple of 3 strings in this case. What are these strings? So they are basically the names of the local variables, right? N is a local variable because it's created as an argument, and the other 2 are local variables because they are assigned in the body of the function. So basically, this is a list of is a tuple that lists all of the names of the local variables, right? There's an inspect module with lots of stuff that you can use to inspect data from different kinds of objects in Python. So, for instance, if I apply the signature function to the Fibonacci function, I get an object that has lots of attributes. One of those attributes is called parameters, and then this gives me a sort of a dict that shows a mapping of the names of the parameters and an object that describes in more detail the parameter. So it tells you if it has an annotation. It also tells you whether it's a parameter that has a default value and what the value is, and so on. Okay, so this is just to illustrate the idea of some of the consequences of handling functions as objects. Well, so one of them is being able to pass functions as arguments, and the other is to be able to inspect, to get information from functions at runtime, right? Okay, questions, suggestions, observations? So let's talk about decorators. The first thing about decorators is that they are syntactic sugar, right? And I think it was what was his name? Famous computer scientist. I think it was Ron Perley's his name, that said that syntactic sugar causes cancer of the semicolon, right? And one thing that I noticed in academia is that many computer scientists, particularly those that are focused in programming language theory, consider syntax a boring subject. So that's why they like Lisp, which is basically a language that has no syntax. Almost no syntax, right? Anyway, I am a defender of syntactic sugar because I think syntactic sugar is something that helps you read. When it's well designed, syntactic sugar enhances readability. And this is one example, because those 2 snippets do exactly the same thing. So the main point here is to show that a decorator is simply a different syntax to apply a function to another function. Oh, let me be more precise. To apply a function to a function object, and that function that's the decorator will return a function. That's the contract. So you apply, a decorator is a function that takes a function as an argument and returns a function. It may actually return the same function. Sometimes it does, but sometimes, more often actually, it returns a different function, right? So another thing that this syntax does is that consider that this is happening in a certain namespace, for instance, at the top level of a module. So this declaration creates a global name, the global name square, referring to this function, right? And this statement here applies this floatify function to square, and then the return function is assigned to the same variable in this namespace, right? So I'm doing this manually. But all of this is implicit in that syntax. So the decorator syntax not only applies this function to this other function, but it also takes the result of this application, and binds it to the same name that was given to the decorated function originally, right? So those are the two parts of the evaluation of a decorator. Is the application and then the rebinding of the name to whatever function was returned by the decorator. Does that make sense? Okay. Now, why is this better? The main reason why this is better is because most functions that we write don't have one line, right? So if you have like a dozen lines of code inside the body of this function, that means that the fact that this function is going to be decorated, it may not be obvious to whoever is reading the function, right? You have to scroll all the way down and say, oh, by the way, this thing is being decorated. And because it's being decorated in this context, it means that everybody else, everywhere else in the program, references to the square name will refer to the decorated function and no longer to the original function, right? So this is important because this is a very important transformation that's happening, and this makes it more explicit. Although the mechanics of what is happening are implicit, the fact that this change is happening is more explicit. Do you agree? Yes.
So if you had
Three decorators? Yeah. Yeah. Okay. This is a very good question. I actually have a slide about that later, but I will tell you just right now. Think about it as if you read this as if there was a parenthesis here, and this function is being passed as an argument to this one. All right. So if you have another decorator on top of this one, this first decorator will actually be evaluated last, because it will it will take as argument the result of this application here, which is sort of what happens when you have multiple function calls in a line, right? The one that's closer to the argument gets evaluated first and then going outwards, right? No, bottom to top. The closest the decorator is to the function, that means it's going to run first. That's the priority, all right? Okay, so the first fact about decorators is that they are syntactic sugar, and that's what they do, right? The second thing is decorators may replace the decorator function with another function. They don't always do that, but most of the time they do that. And you can do a simple experiment like this to see that this is a fact. So I have this decorator here that has this inner function, and this decorator returns that inner function, right? This is just a silly didactic example, so I don't do anything with the decorated function at all. Usually you should do something with the function that you are getting as an argument, but I'm not doing anything here. But so here I apply the decorator to this target function. Okay, so and when I run target, when I invoke target, what I get is the inner result. And as additional proof that target was replaced by that, if I inspect it, the console will tell me that this object named target is actually the inner function of the local environment of the decorator function. Right? So it was really replaced. This target function that I had is no more, and it's inaccessible. and I can't use it anymore. So this is a second aspect. The third aspect that's important about decorators is that decorators run at import time, okay? And this is another thing that's different between, for instance, Python and Java and lots of other static languages, is that, for instance, Java also has an import statement, right? But the import statement in Java is merely a declaration to the compiler. You're telling it, look, I'm going to use stuff that's in this package. So you're just telling the compiler where to find this stuff, okay? In Python, the import statement does that, but the way it does it is different because it's really an executable statement. The import statement in Python means you're telling the interpreter, load this module. And when it loads the module, it will run anything that's defined in the top level of that module, right? So this is an example of a registration decorator that I'm going to show you later. But the mere fact that I'm importing this registration method, this registration module, means that something in that module is running, right? So this is the source code of that registration module. So I have this decorator called register, right? And I have this part here that doesn't run when this is loaded as a module, right? So what you saw in this here is when I did import registration, the interpreter loaded this module, and what happens was, first, it defined this empty list, it defined this function, and then it defined this other function and applied this register function to it. All of these things happened at import time. And that means that because the register function has a print statement that says something, that's what we saw in the console here, right? Or here, actually. See? So the mere fact that you're importing means that user code is running at that point when the import statement is being evaluated. So this, and this is another example where I am running the same module from the command line. So in this case, this is the main module. So what we have is the register function running because it's applied as a decorator to the F1 function. And then you have running top level of module, which is this line. This line shows the registry, and the registry is a list that contains the F1 function. And then it calls the F1 function, and now finally you see it running. Okay? So, is this clear? Because now we are doing an exercise that has to do with that. But this exercise, you don't need to use your computer. You can use any editor. You will not write code, just a few numbers. But let me explain how this exercise goes. So this is a very simple version. It's like a similar to the previous example. So the thing is, if I run this as a program like that, you're going to, there's several print statements that print these angle brackets with numbers. And what happens is the output will show 1, 2, 4, 3. Although the numbers are in order here, the output is not in order. Why isn't it in order? Yes. No, yeah, okay, so, all right. The first one is this. The second one is the application of the decorator. That's what you're referring to, so that's why you have 2, which is here. And then we get to 4 because this is 4, and F1 hasn't been called yet. Sorry? Yeah, so this is a very important point because it means that when the function is defined, function definition is an operation that does not run the body of the function, right? Function definition is an operation that compiles the body of the function and creates an object that represents the function and binds that object to some name. This is what the def statement does, right? Anyway, so let's do an exercise that is this one. So the idea is you're going to write down on a piece of paper. You can do it in pairs if you like. I am a firm believer in pair programming. It's a practice that we do a lot at ThoughtWorks, and we try to convince all our clients to do as well, because it does work. So if you want to pair up, pair up. But the idea is you're going to simulate running main. So if you run main, which is this one, what happens? What is the output that you get? In which order the numbers appear? Okay? So I'll give you 5 minutes, and then I will discuss the solution. And if you want to ask questions or need help, just raise your hand. Yes. Wow, that's weird. Yeah, I have to upload it again. I don't know what happened. So apparently this slide is not on the published presentation. I'll tell you. I'm trying to. It is? Wow. Speaker deck. Yes, it's on speaker deck. Right? Are you on speaker deck? You are, right? Yes, she's there. Yeah, it doesn't appear on hers. It's funny. There you go. This is, yeah, I don't know. Maybe it was a bug on the interface. Yeah. All right. So let's do this. Was it enough time for most of you? All right. So import. So import runs the module. And it doesn't matter if you just mention a single function, right? It has to run the whole module. And then the fact that you just mentioned a single function simply means that only that function will get a name on this namespace. But everything in the module will run. And that means that you get print A. Then you get the definition of the deco function in that module. And this definition does not mean that those statements will run. It just means that the body of this function is compiled and an object is created and bound to the deco name in the namespace of util. And then you get the D. So the first two outputs are A and D, right? So now you have the one from here. And then you have the application of the decorator to this function. And the mere application outputs B, right? And then creates this other function, which is not executed at this time. This is just defined, right? And it returns this inner function. So this inner function replaces the first function here, which means that when first is eventually executed, C will be output, but not now. Right now, what you got is B, right? And then this is, again, just a definition, but then the decorator is applied, so you get B again on the output, right? The third function is just defined, and no decorator is applied to it. And then here we run the first function. So running first actually runs the inner function from the decorator. So now you get C as an output. But this inner function also calls the decorated function, the function that was passed to the decorator. So now you get 2, right? So C2, and this was this call, right? And now the second call. So the second call, again, we are running the inner function, so we get C as the output, and then the F function, which is the name of this guy now, is bound to this guy. We'll run third, so now we have 4 as the output, and then we get 3 as the output because of this print statement, and this ends the execution of the inner function there with this second call, and then we have the number 6. All right? So whenever you're doing metaprogramming, and the subject of our second part, the descriptors, is also a metaprogramming topic, you have to have very clear in your head when stuff happens. And in the Python community, people talk about import time and runtime, right? And so it's really, everything is runtime. That's that's the main characteristic of what a so-called dynamic language is. It means that everything really happens in runtime. But at different stages during this runtime, there are points where there's a special moment of the import time, which is when a module is being loaded, right? So, and the basic idea is that the Python interpreter just reads the module once from top to bottom, defining all the top level objects, and that's it. There are some places where this top-down logic is inverted. One of them is when there are decorators, in which the function definition actually runs before to create the object that's going to be decorated by the decorator, right? Another example is in a class definition. We're going to talk more about that later. But in a class definition, also the body of the class is executed before the actual class is created. Anyway, so let's talk about the simplest kind of registration of decorators that exist. So I think when I was started teaching decorators several years ago, I realized it was a complicated topic, and I was trying to find the simplest kind of decorators that there were, and it just happened that there is this particular kind of decorator called the registration decorators that are simpler, and they are not just didactic examples. They exist in the wild. And what a registration decorator is, they register the functions that they decorate in some kind of global application registry. Like, for instance, several web frameworks in Python use decorators to let the framework know that a particular function is actually a view function. It's something that may be bound to a route that will be invoked when a certain URL is given to the server, and the results, and it will get the arguments somehow extracted from the request, and the result of that function in runtime is going to be wrapped into another object that represents the HTTP response, right? So this is, but apart from all this wrapping that I just described, the mere fact that you are telling the framework this function is a view function is a form of registration. Yes, you want to ask the question? Oh. All right. So I'll give you a very simple example that I invented, inspired by the Click library. Click is a library from Armin Honacher, the author of Flask. And he's a really smart guy, and he decided to create fairly recently this library for command line interfaces. So Click is also a very clever name because he says the Click means the command line interface construction kit. Isn't that awesome? Yeah. Anyway, so it's very interesting. But anyway, this is my example is just inspired, loosely inspired by his library, which is a serious stuff. My example is just very simple. Imagine you want to create this utility, which is completely useless actually if you have a Unix machine, called cron with the K, because everything it does has to do with time. So if you just invoke it, it will give you a simple usage message telling you the options that you can use, D, M, and T. So if I use cron T, it will give me the time, cron D, it will give me the date, cron M will give me the month, okay? So that's very simple. And here's the source code for it, okay? And the idea of using a decorator here is to make it easier to expand, to enhance the utility with new functionality, right? So I think that I have slides that show this. Yes, so this is just an overall view. It's just 36 lines. Let's take a look at the top. So this is our decorator, okay? And we also have this global dict that has that starts empty. But what this decorator does is when you apply it to a function like time, it does three things. First of all, it extracts from the name attribute of the function the first letter and calls it initial. Okay. The second thing it does, it uses that initial as a key and puts the function that was received in the dictionary, right? And the third thing is it returns the function itself. And this is crucial, actually, because the decorator must always return a function. After all, it's going to replace the decorated function with something. And that something is better be callable, otherwise your program is going to break real soon, right? So in this case, it's just returning the decorated function itself, which means it's not changing its behavior at all, right? So then I apply the command to another couple of functions, the day function and the month function. And so in our main function here, what it does is it gets from the top level code here, it gets the command line arguments, right? And it checks if there is more than one argument, and argument 1 is one of the keys of the commands dictionary, then it will retrieve that key, use that argument as the key to retrieve that command and call it. See? And this is something that sometimes is surprising for people who haven't used functions as objects before. The fact that you are retrieving an object from this dictionary and then calling it, this pair of parentheses here, right? So sometimes it helps if you think of the parentheses as the function call operator, right? So this expression here produces an object that is a function, and then the parentheses execute the function. Otherwise, it means that either the person did not pass an argument, because argument 0 is the name of the program. So the person didn't pass an option, or the option was not in the dictionary. Then you just print the usage message. And what I'm doing here is I am just putting the keys of the commands type dictionary sorted and separated by types. So this is what produces this message here, right? So the keys of the dictionary separated by types. This is what this line is doing. Oh, okay. So the F is a brand new feature of Python 3.6. It's called it's an F string. So what are F strings? So for the first time in the history of Python, we have executable strings. So there's a question? Sorry. The function call operator. No, it is, you can actually consider them that, because there is, for every operator in Python, almost everyone, there is a dunder method in the data model that is something that you implement if you want your objects to support plus, for instance, the plus sign. You create a method called dunder add. And dunder call, exactly, right? You're welcome. So let's go back to F strings. So the idea of F strings is that, so for the first time in Python, we have executable strings in the sense that before F strings were introduced, whenever you wanted to do string interpolation in Python, you either use the percent operator or some functions like the format function and the format method. But now, what you have is this F syntax where you put this F prefix in a string, and then it will evaluate everything that goes inside those curly brackets as expressions in a limited syntax that does support, for instance, indexing. It supports just retrieving a value in the local namespace and so on, right? So it's the same. It goes as far as it's the same rules that we have for variable lookup, and I'm going to talk about that soon. Yes. 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 And at the very end of this part, I'm going to talk about that. Some of the leading authorities in decorators in the Python community advocate that decorators should be implemented as classes. Okay? But I'm going to talk about that later. Yeah. So, here's the thing. Let's try and do this as an exercise. I don't know, maybe I think we are running late, so let's not do this as an exercise. Okay. So what I'm going to do, I'm going to just show you how to extend this, okay? So the idea of using a decorator here is to make it easy to extend. And now suppose I want to add a Y command line option to the utility. So that becomes really easy because all you have to do is add this function, right? And the interesting thing is this could be a huge program with hundreds of modules, and this definition could be anywhere. Because whenever that decorator is applied to a function anywhere in the program, what it does is it adds that function to a dictionary that is a global variable of this particular module. Right? And this is an interesting thing that it took me a while to realize this. The concept of global variables in Python is not the same as in some other languages. Because in Python, we don't have truly global variables because namespaces are more important than global variables. Every variable in Python belongs to a specific namespace. So every module has its own global variables. Does that make sense what I'm saying? So a global variable in a module is a global variable in the program as a whole because it exists while the program is running. Just the same in the same sense that the module exists while the program is running, right? So these variables last forever, but they don't trample each other in a single global namespace. They are global variables of particular modules, right? So this is interesting, and it's very clean, and it makes this solution that is really simple suitable for a much larger program. Does it make sense what I just said? Please ask questions if not. Okay, so let's talk about variables now. Because, okay, so if given a clean environment, and you can try this out on the Python console if you want, just open up the Python console and define this function, f1, for instance. So if I have this function f1 that gets a as an argument, and I do print a, print b, when I call it, I get the output of print a, which is this number 3 here, but then I get an error because the global name b is not defined. All right? There's nothing surprising about that. Afterwards, in the same environment, I can assign a value to b. So now I have a global variable b. And now I can call f1, and I see the output of this print and that print statement. Okay? No surprises here, right? Now, here's something that's surprising. This function will never work in Python, regardless of the existence of a global variable called b. Okay? And the interesting thing that you see is you get the output of print a, and notice those are the same two lines of the other example, right? But now, even though there is a global variable b, this print doesn't work anymore. It used to, but now it doesn't, right? And the message that you get is different. Unbound local error, local variable b referenced before assignment. So what happened was, and here's the thing, you have to understand, and this has to do with import time and runtime again, that the history of a function has two moments: when it's defined and when it's invoked, right? When a function is defined, that means really that Python compiles the bytecode of the function. And when Python does that, it decides that b is a local variable because it's assigned in the body of the function, right? So, although you may think this is a little bit weird, a famous alternative to this, which is the way JavaScript handles variables, shows that this is really very clever, actually. Because the way JavaScript handles variables is, if you don't write var in front of an assignment, then you are creating a global variable all the time, every time, right? And Python doesn't have this way of declaring a variable in a context, saying var, but it assumes that if the variable is assigned in a local context, then it's a local variable, which is a good assumption that works for us most of the time. That's what we want, and it's a very well-designed feature. But in the book, I actually I show the disassembly of this code, and then I show that the instructions for retrieving this b are not the same as the instructions for retrieving this b. So Python has a module called dis, which DIS, so it is a disassembler module, and what it does is you give it a function, and it will show you like an assembly sort of listing of the bytecodes, and you can see that the code generated for this function, the second statement is different from this statement, because in that one it retrieves a global variable, in this one it retrieves a local variable. Okay? So that's the idea. So one way of dealing with this is this declarative statement called the global statement, which we rarely use, but it solves this problem here. I want to tell the interpreter that even though I am assigning a value to this variable, it's really a global variable, right? It's one of the few declarative statements in Python that declarative in the sense that they don't execute user code. They're just there to tell the interpreter something. Right? Okay, so now that we understand this concept of local variables in Python, we can talk about closures. And here's the first tip. The first time when I was trying to understand what a closure was, I was studying on the blogosphere about closures. And that didn't work so well for me, because I read a lot of stuff about closures, and nobody used a magic term that I'm going to introduce to you that makes closure suddenly clear. Okay? And another thing that's confusing is, in many places on the web, people confuse closures with anonymous functions. Okay? No, anonymous functions is a syntax detail. The fact that there's a way to define a function without giving it a name immediately is just a syntax detail, and it's not as important as the concept of a closure. The reason why those two concepts are conflated is because most of the time, when you're defining functions inside other functions, those inner functions in other languages are usually anonymous functions. And it's when you have functions inside functions that the whole issue of closure makes sense. So what happens is most people are exposed to both concepts of anonymous functions and closures at the same time. And that really creates a confusion, because I've actually read some really important people on the famous people writing that closures are anonymous functions or anonymous functions are closures or something like that, like as if they were the same thing, and they are not. Okay, so here's an example. It's a kind of it's inspired on a classic example of functional programming to explain closure. So the idea is, imagine I have this function called AVG that computes the running average of a series of values. This is a series that is always growing. Like, for instance, the closing price of a commodity. Every day I want to add a new value to this series and get the historic average for the whole time, right? And this is kind of a crazy function that keeps state, right? Because when I call it the first time, the average is that value because it's the only value in the series. But then when I call it a second time, it takes into consideration the previous value, and calculates the average, and so on, okay? So every call to average adds a term to this historical series and then calculates the average, okay? So you can do that as an object as a class, just an average, just an object. If you use the call method, and this is the whole solution. So what I'm doing here is I am creating an instance of averager, and the averager has an instance attribute called series that starts as an empty list. But the thing is, the result of this call is an instance of averager, and instances of averager respond to the function call operator, which is the open close paren, because they implement the dunder call method, right? So if you haven't read my book, this whole issue of special methods is one of the main themes of the book, but the first chapter is free. You can download on O'Reilly, the PDF for the first chapter, and I really like that chapter because it's really an overview of this whole idea of special methods that explains a lot of stuff in Python. And I just give this brief introduction in about, 18 pages. So anyway, so the dunder call method is what makes averager instances behave as if they were functions, right? So you can call the instance, and every time you call, what we are doing is we are appending the new value to the series, then we are computing the total and calculating the average by dividing the total with the len of the series, right? Simple? Okay, so this is one way of doing that, and the other way is using a closure. And if you notice, this here behaves exactly the same. The only thing is that instead of calling the averager class, you're calling this makeAverager function. And so basically, when you explain classes in beginning, in beginner object-oriented courses, we like to say that A class is like a machine that makes instances, right? You can even use the word factory or cookie cutter or whatever, right? It's some device that builds other objects. And the thing is, you can use a function to create something that behaves like a function, right? You can use a class to build something that behaves like a function if you implement the undercall method, or you can use a function by doing what? By defining a function and returning it, right? So this behaves the same way as the other example, okay? Now, the thing is, here, it's explicit, the whole handling of the series data. So the series data is declared as is created as an instance attribute, right? So each time you call averager, you get this particular AVG object, and you can have several of them at the same time, and each will have its own state, right? Each will have its own series attribute. But here, things are not so clear, because what happens is this guy is referring, the body of this function, which is the function returned, is referring to the series variable here. But isn't that shared by all the instances? Looks like it, but it's not actually. So this is where we actually introduce the concept of closures, okay? So the idea is, and here's the key concept, that after reading several, after I read several blog posts about closures, nobody used this magic word. The magic word is free variable, okay? So this is a problem that anybody that designs a language that allows functions to be defined inside other functions has to tackle the problem of the free variables. And so what are free variables? Free variables are variables that are not local to the function. See, this function here, how many local variables does averager have? 2. One is total, but the other is the argument. Every argument is a local variable. Just think of them as local variables. They are represented, they are stored the same way as local variables, okay? So you have 2 local variables, and series is not one of them. So in the context of this function, series is a free variable. Because you know the concept of binding, right? So a variable is a binding between a name and a value, right? And a free variable is a variable that's not bound to anything in this context. You don't know what it's bound to in this context, right? So the problem is that in this case, series is a local variable of this other function, this outer function. However, this outer function, when invoked, returns an instance of this inner function, right? Returns, and when I say returns, it means not only it produces that value, but also that its execution returned. So it's terminated. The local context does not exist anymore. But you have assigned, you may have assigned, like I did in the other example, I have bound, so calling makeAverager returns an averager function that I am binding to this AVG function. So now what happens is I have the AVG function, which is really a reference to the averager function, but this context of inside the makeAverager doesn't exist anymore. So how does Python resolve this, the free variable series when you actually invoke this function here? And there are, in the history of computer languages, there are 2 solutions to that. The first one is the simplest one for the language implementer, and was the one used in the classic original Lisp interpreter that John McCarthy wrote as a paper. Is also the original way that Perl handled variables, and it's called dynamic scope. And dynamic scope means that when you call the function, it will try to resolve that series by looking out from this scope here, which means if there is a series variable that was defined before, it's going to use that variable. And that's easy to implement as a language implementer, but it's really bad for the programmer, because it means that the function is no longer a black box. Its behavior will change depending on the existence or not of certain variables in the environment where it's called. And that's weird, okay? So after a while, language designers agreed that the best solution is called lexical scope. And lexical scope means that the scope of variables must be determined by just looking at the static source code. Which means that because this is referenced, which means that this free variable must be resolved in the context where you know for sure that there is this other variable, there is this binding to this same name. So basically the closure, what it does is, wait, where is the, I have to tell you guys this. I'm trying to get rid of macOS. I'm using Linux on another machine, so I started using LibreOffice on the Mac, and I don't know, but on the Mac it loses slides. It moves them around. So that's why when you were complaining, I thought it was my problem, because this is happening all the time. Anyway, I promised I did have a slide that was showed that the closure is actually an extension of the scope of the variable to encompass the free variables when it's defined. Okay, so the key drawing that we are missing here is just another slide similar to this one, but with a box around this whole area here, saying this is the closure. So the closure includes the function definition, but adds to it whatever free variables are mentioned. Okay? And in practice, this is a data structure that you can actually inspect. See, the AVG object, which is actually an instance of averager here, has an attribute called under closure. And if you inspect that, you will see the numbers of the series. See? I don't have time to go into much detail now, but I'm just showing you that the values are there. The names of the name of the free variables are here. See, free vars, and var names is another attribute that I already mentioned before. So anyway, so the closure is really this: is a data structure that extends the scope of the local variables in a function to encompass the free variables, so that when the function is invoked later, it has access to those values. Okay. And another thing that's interesting to know is the fact that although this definition exists only once in the source code, right? Every time makeAverager is invoked, a new instance of that function is created. Does that make sense? So, and each one of those instances will have its own closure, and therefore it will have its own value for the series variable. So each one will have an independent state. Okay? So, yeah. But Python is smart enough not to duplicate unnecessarily information. So what it does is, when you have the decode attribute, the decode attribute stores everything that is static that is unchanging about a function definition. So the variable names never change, right? The free variables never change. They are just results of inspecting, of parsing the code, right? So everything that belongs in the decode attribute are attributes that are static, that every instance of averager will share those same attributes. But a specific instance has a closure attribute that is different from the others. And that's why the values are here and the name is elsewhere, because the name is always series, but the values are different for each different instance of the function. Okay? Questions? Yes, go ahead. Uh-huh. Yes, exactly. Yeah. Yeah, exactly. The closure is sort of a tuple that runs in parallel with this other tuple, right? Because the names are here and the values are here, right? So maybe we could have three free variables here, and then we would have closure 0, 1, and 2, which are the cells for each of the variables, right? Oh yeah, sure, yes. Yeah, it's a list. Yeah, exactly. Yeah, it's a list. It's not a tuple. Yeah. Mm-hmm. It says here cell, no, list object that, yeah. No, actually the list object is the series. This is what it's talking about. Yeah, it's the cell object. So I don't know about the cell object. It's not something that is exposed to us users of Python. It's an implementation detail. It's probably written in C, this data structure. Yeah, I don't know. Maybe, yeah, okay. Now, here's the thing. This implementation of the averager works, but it's inefficient because you don't really need to keep all the series to compute the average, right? So you could do this, but this doesn't work. Why doesn't it work? Sorry? That's a very interesting way of putting it, but I will try to use the same terminology that I was using before. And the terminology is that this operation creates a local variable. This operation is actually a shortcut for count equals count plus 1. And assignment always creates a local variable. Why didn't we have this problem before? Because we didn't assign to series, which we used the append method to change it. Yes. 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 Even before, like in the other example, even before doing this operation, it will break. If you just try to print the current count before this line here, like right here, it would still break with the same message because when the body of this function is compiled, Python decides that count is a local variable, and it will try to retrieve a local variable called count before it exists. And this is what is happening implicitly here, because if you think that, realize that count is actually count equals count plus 1. So on the right side, it has to first retrieve the value of count. And when it tries to retrieve the value of count, it discovered that there is no value for count. Just a parenthesis, because Guido is a genius, and he didn't provide us an undefined value, right? It's one of the stupidest creations in the entire history of programming languages, an undefined value. Go ahead. Yes, your question. No, you couldn't, because these are not called global variables. So in order to fix that, you have to use a new statement that was introduced in Python 3 called non-local. Okay? No, it won't. It will still behave in a lexical way, meaning the traversal is through the source code and not through the state of the running program. So, yeah. So that means that if you say non-local here, it will just look into the source, looking at the source code, see, so where is this defined? Okay, this is where it's defined. I am not sure. I haven't ever done that or tested that. Sorry? I don't know that either. I never use, the thing is, we never use, not never, but we rarely use global, right? And so I don't know, actually, if you mention a global variable that was never defined before, what happens? But yes, please do. I wanna try that as well, so let me try it. No. Yes, you get a name error when the program is executed. Yes. It's different from, yeah. Yes. Yes. Mm-hmm. Exactly, yeah. Yeah. Anyway, so that's why non-local was introduced, was to solve this little problem. And if you're stuck with Python 2.7, you should be trying to find your way out. But if you're stuck with Python 2.7, the way you do this, you usually you create a dictionary, for instance, called environment or whatever, and put it here, and then you modify it using you use it, basically what you are going to do by hand what Python does for you automatically, which is every environment is a dictionary that maps variable names to values, but you can do that with a dict. And so when you assign to a position to a key in a dict, that doesn't really assign to the dict variable. So it also works. It's another way of doing this. It's similar to the reason why this was working before, because you can change. You can change it's a mutable structure that you can change without reassigning a value to it. Okay, so this works, and now let's talk about functional decorators, which are decorators that actually replace the function with another function. Okay, so this is a very simple example of a function that, a decorator that transforms the output of another function into a float. Okay, it's just a stupid example, I'm sorry, okay? So how does that work? For instance, if you define a function square and you pass it an integer, you're going to get an integer result. But suppose I want always float results. So you can create this decorator called floatify. And so when you decorate the function, you call it, and now you get a float result. But you have this problem, right? That when you look at what square is, you don't see anymore the name square and the reference to the other function. You get this floated function. And this is the definition of the decorator. So basically, this is very simple, but still typical of a decorator that changed the behavior of another function. So the decorator gets the function as an argument. The inner function gets whatever argument the functions to be decorated are supposed to get, right? So in this case, this can be applied to any function that gets that receives one argument. And now what I do here is I run the original function, and the reason why I can refer to it is because it's part of the closure, right? So I run the original function and I store the result, because sometimes I need to do other stuff. In this case, I just want to apply float to the result and return that value, right? So this is the definition of the inner function, and this is the function that I return. So I return the inner function, which is the function that's going to replace the other one. So I get so when you apply this decorator, you get this floated function, and that's what we are seeing here, okay? So some things that you have to address when you do a decorator that changes the behavior of a function is, first of all, the replacement function usually should honor the contract of the decorated function, meaning it should accept the same number and types of arguments, and it should return a compatible value, right? So that it can be used in the place of the other. But the reason why I say usually is because a very common example of behavior changing decorators are the decorators that I mentioned before that are used in web frameworks, where you decorate a function to be a view. And one of the things those decorators usually do is they completely change the type of the result. Sorry. Wait. Okay, so for instance, this helps you a lot in those frameworks, because you can return a string and it will wrap that string into a response object that has HTTP headers and so on and so forth. See? So the type of the return value is being changed by the decorator, but it's being changed in a way that's useful to you. Okay? I particularly like that, for instance, a framework like Pyramid allows you, for instance, to return a dictionary in a view function, and then when you're writing unit tests, you can test that the return was a specific dictionary that you were looking for. But then, if you have a decorator that says that this function will return a JSON object, so it will actually create a JSON response and do all the marshalling necessary and so on. So when the function is actually integrated in the framework and it's exercised through a URL, it will return a JSON string. But when you're doing unit tests, it's smart enough to know that it's easier to test just a dict than a string that looks like a JSON object. Does that make sense? So that's the reason why I'm saying that usually. Depending on the type of decorator that you're using, you should respect the contracts of the function that you are decorating, but sometimes the whole point is to, like, for instance, change the return type or something like that. Okay. The other thing is the replacement function should preserve metadata from the decorated function. Okay, and that's useful particularly for debugging and other metaprogramming purposes. But that, fortunately, is easily done using a decorator. What else? That comes in the Python standard library, the functools wraps decorator. So what you do is you import this wraps decorator, and this wraps decorator you use to decorate the inner function that your decorator is going to return. All right? And you explicitly pass the function that you are decorating to it. So what you're saying is, this inner function wraps the behavior of this f function. You see, it's true because this is what's happening here, right? You're calling the f function. So when you do this, what happens is, when you inspect the decorated function, you get the name of the original function. And if you do help on it, you get everything. All of these things that I'm doing would not work without the wraps decorator, right? Because this would return a reference to the inner function, the floated function. This would give you whatever is the docstring of the floated function, but this is all working because of that wraps decorator, right? So basically, the wraps decorator copies the metadata of the wrapped function to the wrapper, which is the inner function. Yes. Yes. Mm-hmm. That is confusing, but we have slides to try and unconfuse that. Okay? But it's a very good point. It's a very good point. Most of the decorators we used before did not have an argument. And the reason why this is confusing, that's a very smart observation, is because when you don't have an argument, the other kinds that we've seen, is you can read this as this function will get this other function as the argument. Right? So, but what happens in this case? I will answer that soon. Okay? No, actually, I will answer it now with a short answer. This actually is not a decorator. Wraps is a decorator factory. It takes this argument and returns an object which is a decorator and which is then applied to the rest of the function. We are going to see the source code of that later, but that's the idea of how you implement decorators that take arguments. Basically, a decorator that takes arguments is not really a decorator. It is a function that will return a decorator suitably parameterized. Yes, exactly. So but I'm going to show you source code that explains that. Okay, so let's talk about a more useful example of a decorator that is something that you could use to time and trace the execution of a program. So this is the clock decorator. And what it does is, when you apply it to a function, it will show, every time the function is invoked, it will show the elapsed time of the invocation, the name of the function, the argument that was passed, and the result that was received, that was produced, okay? So in this case, we have the snooze function is a function that just sleeps for a while. So it got this number, so it should sleep for 123 milliseconds. The execution of this actually took 128 milliseconds, and the return was none. In this case, we are running factorial several times, and we are seeing, we are running factorial 6, but it's a recursive definition, so then we get all the other results. And this is an example of the clocking decorator. So it's a little bit more substantial example of a decorator. So what it does is, again, we have the wraps decorator so that the whole metadata of the decorated function is preserved. And this is not very interesting. What is more interesting here is the fact that I take the original time, I execute the function, passing the arguments that I got, and then I can compute the elapsed time. I get the name of the function that I decorated, and then I build this string, which is this string here, okay? So basically the elapsed time and the function name, the arguments, and the result, okay? So parameterized decorators, and yeah. But we are at the break time, so let's go for a break, and then we come back to parameterized decorators, okay? So let's get back. So we already touched on the subject of parameterized decorator. We are running a little bit late. I should have finished this decorator talk before the break. But I really believe that it's good and useful to emphasize those basic concepts of functions as objects and closures in particular, because otherwise this whole thing is just magic. And so I don't regret that we spent all of the time with that. Because what happens now is things get more complicated, but it's pretty much more of the same, more levels of the same. So in order to do a parameterized decorator, like, okay, so this example, this would be a version of the clock decorator that allows you to pass a string to format the output of the log. Remember? Remember that this clock decorator produced output like this, and maybe you want to change the appearance of that. And so this is the idea here, that you can now pass a format string that is going to be used to generate the trace lines, okay? Now, one thing about parameterized decorator is that if you don't want to pass a parameter, you still need to call it. Different from other decorators, right? Because the fact is that parameterized decorator, like I said before, are really decorator factories. They are functions that when you call, produce a decorator. So notice that the parameter on a regular decorator, like this one, a regular decorator always receives a function as an argument, right? But the parameterized decorator receives whatever parameter it has to receive, and it returns a decorator, which, just like a regular decorator, receives a function as an argument. So does that make sense? So that's why you need to call it, even if you're not passing parameters. Because calling clock, even without arguments, what this does is it returns the decorate object. And the decorate object is a real decorator that will get the snooze function as argument here. Okay? So what you get is this other level. And that's and we don't want to get confused, so we are going to squint and pretend that we are not seeing this other decorator here, right? Because it's another level, and this is also a parameterized decorator. So it's really turtles all the way down, you know. Anyway, so let's talk a little bit about ready-to-use decorators in the standard library. Oh, by the way, if you're really clever with Python tricks, you can actually do a decorator. You can actually implement a decorator that works in this situation with or without the parentheses. And actually, David Beasley, who is one of the cleverest guys around in the Python community, does that. In the Python cookbook, he has an example of a decorator that behaves in, you know, in both ways, but it's complicated. It will get called with the function. So what it does is it notices, oh, okay, they are passing a function to me. So I'm going to assume that he wants the default arguments, and I'm going to decorate this function. It's sort of what it does. Okay, it's interesting because this kind of trickery is not used in the standard library of Python. Okay, it's possible to do, but it's not something that the actual people who do the standard library of Python decided it was worthwhile to do. So here's some famous decorators in the standard library. There are three built-in functions: property, class method, and static method, which are designed to be used as decorators, right? There's the functools wraps, which we already saw. The functools single dispatch is awesome, but I don't have time to explain it now, but I suggest you read about it. It's really interesting, and it's a trend that is appearing in other. This idea of single dispatch mechanism is appearing in other languages, like the Julia language, which is a scientific computing language that gives Jupyter the GU syllable. The Jupyter project is named after Julia, Python, and R. And Julia is a language based on this idea. Single dispatch is really interesting, but I don't have time to. This is actually a class decorator. If we have time, I'm going to show you class decorators later. But and this is very interesting. This I'm going to demonstrate. So the idea is this. Previously, I had shown another Fibonacci function that was a Fibonacci function that was iterative, and this one is recursive, and it's really stupid because it's really exponential time. The time complexity is exponential, so it's useless, but it's very useful to demonstrate things that handle delays, right? Or things that make your code go faster. So, for instance, this is a trace using clock of calling Fibonacci 7. So this will give you the number at index 7 of the Fibonacci sequence, starting at 0. And look how stupid this is. See? It's actually calling 13 times Fibonacci 1. See, each of these recursive calls eventually will call Fibonacci 1, and multiple times. So it's really stupid. It takes 41 calls total to get to what is really the 8th iteration of the series. Okay. Now, here's some magic. LRU cache. LRU stands for least recently used. So it's a cache that preserves the values that were more recently used and discards the ones that are older automatically. You have to call it like that because it accepts parameters, including a parameter that tells it how many values it should store in the cache. But it has some sensible default. And just by adding this one line, suddenly this becomes usable. It's just performing one actual call. Because what this does is basically it creates a dict with the arguments. And if the function was already called with that argument, it's going to just retrieve the value that was previously computed from the dict. So it's as simple as that. And it's something that's in the standard library. So it's reliable, well-tested. Use it. And this is an example of applying two decorators, one on top of the other. Yeah. So, okay, I'm gonna leave this as homework for you, okay? But I promise, if you write to me, I will help you solve the problem if you have difficulties, okay? I will give you my email soon, but the homework is, it's in the repository there is exercises /cron 2, so it's the source code of that cron example, and there's also a simple test, and the idea is to transform cron, the command decorator, into a parameterized decorator that allows you to pick the letter for the option. Remember how the logic was? In the original cron example, I just used the first word, and that's a problem because maybe you have two functions that have the same initial letter, but you want to assign a different letter to the command line option. Does that make sense? So that's the idea. Try this exercise. It's not very difficult. There are tests. So you start by copying the stuff, and then you make the change so that the command decorator accepts a letter as the argument. Okay? So homework for tomorrow. Okay? Class-based decorators. This is just to show you that such a thing exists. Okay? And this, so we have this parameterized decorator here that has these 3 levels, right? So the outer level, like I said, is really a factor that produces a decorator. And this is the decorator that takes a function as an argument, and this is the inner function that replaces the decorated function. So you can actually implement that using a class, and this is how it looks like. Okay, so again, think about the fact that the clocker class is a decorator factory. When you invoke it, and this is an example of a parameterized decorator. So when you create an instance, you pass whatever parameter customizes its behavior, in this case the format string, right? And now you get an object that is a decorator. And this decorator, like any decorator, when called, takes a function as an argument. See? I implemented under call method. So the instance of clocker is a decorator, and it takes a function as an argument, and it produces another function that will replace that function, the decorated function, right? So if this wasn't a parameterized decorator, if it was just a simple decorator, you would not have any nested function, because the role of the outer function in a regular decorator, which is to accept the other function and return another function to replace it, would be made by the clocker instance. And so you wouldn't have any nesting of definitions like this. The call would be actually the function that replaces the other. Anyway, so it's a possibility. But the thing is, you really shouldn't be. This is just the idea of the source code and these examples was to explain how these things work. But for doing, if you actually want to use decorators in your own projects, implement decorator in your own projects, you shouldn't be starting from scratch. I strongly advise you that at least always use functools wraps, but even better, use one of these libraries from these guys. Graham Templeton wrapped package, and Michele Simeonato has the decorator package. Both are packages that allow you to create much better behaved decorators with solving lots of tricky problems for you. Okay. So this is the homepage of the wrapped module. And of course, what it does is, one of the things it does is, it gives you a decorator to decorate your decorators. See? There's the wrapped decorator, which you use to decorate your decorators. And when you so decorate them, they will work better. Okay? And this is the Click homepage for the Click project that I mentioned before by Armin Honacher, that uses lots of decorators to create command line interfaces. And so this is my Twitter handle and my email. And if you want to do your homework, do your homework, and I promise that I will answer questions. Okay. So let's move to the other subject. Any questions about this subject or any observations? The other subject is also interesting. And no? Okay. So for the other subject, I have another presentation that is also, I don't know, I'm just addicted to fake news, guys. Speaker deck, / Ramalho. So this is the one that we just saw, and this other one is what I'm going to use to explain decorators or descriptors for you. Okay, so let me find that. Sorry, yeah, Python-descriptors, yes, is the URL, but you can also click, just go to speaker deck / Ramalho and click on the second okay, so this is another, so the decorator syntax and the semantics of it is pretty uniquely Python, and this is another thing that's pretty much uniquely Python, the idea of descriptors. And basically, let me give you a little bit of context. Who uses Django here? Yes. Mm-hmm. Oh, I see. Maybe I can take this off, I don't know. All right. So, who uses Django? All right, about half of you. And the thing that led me to study this subject several years ago was that one day I was looking at this code, and I said, you know what? I don't really understand what's going on here. What is this? What is this? You know, I'm creating, this is a class attribute, all right? Because I am assigning a value to the namespace of the class. You what? The phone. All right, thank you. Sorry, Bill, or Brian, sorry. So I am creating this class attribute, but I am instantiating this other thing. What is this other thing? You know, it's funny because I had already been using Django for a few years before I realized that I don't understand what this code is doing. You know, if you don't think too hard about it, it's pretty obvious. It's creating a char field and this other char field. All right, okay. But really, what is going on? This char field class, what does it do? You know, and how is it that this thing that's a class attribute suddenly becomes accessible through the instances of that class? Right? When you assign to an instance of the class. I always thought that when you assign to an instance of the class, that takes priority. And it does really, usually. What I mean is, and what I mean is this. Let me show you. So if I have a class, I don't know what's going on. Again, the noise. Sorry, guys. So if I have a class dog, and it has paws 4. Okay. So I have Fido, which is a dog, and Fido paws. But really, I'm actually reading a class attribute here, right? They're the same thing. Now, if I do Fido, sorry, Fido had an accident, okay? A very unfortunate accident. It's still a happy dog, playful, but it has 3 legs, 3 paws, okay? So now, Fido has 3 paws, but the dog class still has, 4. So really, when you set a value in an instance, it overrides. It doesn't override really. It just creates that value there. And when you look it up later, it's going to find that before it finds the class attribute by the same name, which is kind of logic and it makes sense. Okay, but once you observe this, you can't really explain how is it that if you have Joe, this instance of person on your hand, and you assign to the name, this whole mechanism gets into play. You know, you say Joe.name or Joe.firstname equals John, and somehow this is actually going to be executed, or some mechanism. So this is the explanation. The rest of the remaining, how many minutes? 40 minutes is the explanation. Okay, so we're going to have to be quick. It's 4:20, right, that we finish here, is it? Yeah, all right. Okay, so anyway, so I'm gonna skip this because it's not really important, but so suppose I want to create this customer class, but I want this customer class has name, email, and a certain fidelity points, so an attribute that has fidelity points. And to happen. I don't want somebody to be able to create a customer with an empty email, because then when I call this full email method, it gives me an invalid email, right? So what I want is this. If somebody tries to create a person with an invalid or an empty email, it raises an exception saying email must not be empty, okay? So what I do is I transform this into a property. And so the way I approach this is by showing you diffs. All right, diffs generated with MELD, which is a diff program available for Linux. And so what I'm showing is this part here is the doc test. And what changed is before you got this result, now I want to have a traceback. So basically, a doc test. Who would like me to explain doc test really briefly? Doc test? No? Okay. Yes. All right. So basically, a doc test is a string that has indented bits of code that emulate a console session by using the three greater than signs here, this prompt. And so Python has a module called doc test. So if I run, so for instance, this module is called customer.py. So I can call Python -m doc test customer.py, and then it's going to run the doc test module on the customer.py. And the doc test module, what it does, it looks for doc strings that have this syntax and executes them and checks whether the output is exactly the same. So this is really awesome because it guarantees that the documentation embedded in the code describes the behavior that is actually implemented. And I also find it useful as a teaching tool, not only for checking the documentation. And for designing APIs, I like it too, because it forces you to think on how an external user is going to interact with your API. But anyway, yeah, I want these things to happen. I want to see this error, and I want to see. I also want the error to happen if I try to access to assign directly to the attribute, not just by calling the constructor, but also when I assign. All right, and I also want to check that the type of the value passed is a string and not a number or something. Okay, so how is that implemented? One way of implementing it is using the property decorator. So the way you use the property decorator is you decorate a method that has the name that you want, the public name of the property that you are defining, right? And this is something that's interesting, and it's fortunate that we just had a class about decorators, because now you can understand what happens here. Is this decorator turns email into a special function that also has an attribute called setter, which is a decorator, right? So basically, this is the getter and this is the setter. So this is the code that's executed when somebody reads customer.email, and this is the code that's executed when somebody tries to set customer.email equals whatever, right? So the getter and the setter, right? And this trick is important because this is what establishes the relationship between these two guys. This is the setter for that property. And by convention, you use this name here, but I don't think Python cares about this name. You could put anything, right? The relationship here is established by, okay, this name is important because this is the name that defines the public name of the property, but this one is not relevant, and by convention we use the same. Okay? So this is the property mechanism. It's pretty simple to use, but there's a problem. Suppose I want to apply the same rules to the name attribute. Basically, I would have to copy and paste everything again, right? And this is the problem that descriptors try to solve, is to create a mechanism to handle attribute access, a generic mechanism to create getters and setters that you can reuse. This is the whole idea of descriptors. Okay, so how do you create a descriptor? Basically, you create a descriptor, and this is interesting because I find some parts of UML useful. And one thing is I'm trying to show here is, for instance, this is a high-level definition of the customer class. And what I'm saying here is that it has 3 attributes, name, email, and fidelity, where name and email are descriptors, okay? But I'm not showing the details of how this is implemented here, okay? And how do you create a descriptor? Basically, a descriptor is a class that implements a dunder get or a dunder set method. Okay, so this is a descriptor. So any class, it doesn't matter where it comes from, where it inherits from, any class that defines either a dunder get or a dunder set method is a descriptor. Okay, and how do you put those 2 things together? So actually, I'm going to rewrite this UML in more detail, right? Because here I'm just giving you a high-level idea that this name is a descriptor. But what I'm really saying is this, that customer, besides a simple fidelity field that's not interesting for us, it has 2 class attributes. The underline here means class attributes. And each of those class attributes is an instance of the non-blank class, which is a descriptor class. Why is it a descriptor class? Because it has a dunder set attribute. Method, actually. Okay? And this actually is an overriding descriptor. Why is it an overriding descriptor? Because it implements dunder set. And what does it mean that it's an overriding descriptor? It means that it overrides that behavior that I just described when I showed the dog and the paws. Remember? The fact that you can assign directly to the instance with no interference from the class. This is the normal behavior, but if the class has a descriptor that is an overriding descriptor with that name, like the name paws, then the overriding descriptor takes over the process of assigning to the instance. Okay? So this is powerful stuff. Now okay, so when I was trying to explain these teaching classes years ago using just UML, I found this really confusing because I discovered that UML was really designed for more static languages. And in dynamic languages, you have this thing of instances that are created at runtime that are attached to classes, which are really more static stuff that is in the source code. And UML is not very good to describe that. So I decided to complement UML with little drawings of my own. Okay? So the drawings here show that there is a customer class and a non-blank class. And in my notation, my rigorous notation, classes are machines that produce instances which are much simpler, obviously, right? Yeah. Anyway, so these are instances of customers, and these are instances of non-blank. okay? And the reason why I had the necessity of drawing this like this was to make clear the distinction between instances and classes. Because what happens is that the customer class has two instances of non-blank attached to it. And this is the crucial relationship that is difficult to represent in UML. Okay? Because guess what? In UML, classes are represented as rectangles and instances also. So it makes it hard to understand what's going on. So in this case, it's obvious. Those are instances because they're not machines. This is a machine. Okay? And now if I annotate that UML diagram with these pictures, hopefully it's easier to understand. Right? So you have this class definition here, this other class definition, and what happens is that this class has two instances of that class attached to it. Okay? Okay, so let's look at the example, at the code. First, let's look down here, because this is the fun part. And this looks like Django modules, right? Now you have this thing that is obviously a class attribute, and you're saying that it's an instance of that, okay? Now, Django is cleverer than my program here because you don't have to repeat the name of the attribute. We must repeat the name of the attribute. I will explain why. But we are going to fix that in a later version. But now, so what happens here is that, so this is an instance of non-blank, and this is another instance of non-blank. Two different instances of non-blank. And this is the definition of non-blank, okay? So, when you create an instance of non-blank, you have to pass it this name, which is what I call the storage name. And what is that? That's the name of the attribute in the instance of the class where this descriptor is going to be used, where I'm going to store the value, for instance, of the name or of the email. Okay, I have to store this in the instances of that class. Because, for instance, suppose I have 1 million customers, then I have 1 million instances of this class, and each of those instances will have a name, and each of those instances will have an email, right? So, this is important to understand. Although the descriptor is a class attribute, it stores a value in the instance, right? So you have 1 million customers. You have only one customer class, which is the machine that creates customers. You have only one instance of that. And in this instance, there is this relationship with the two descriptors. But the descriptors, when activated, must store stuff in the different instances. Does that make sense? And that's a very important, very good question, because it goes to the heart of what I'm trying to explain. That you want this mechanism, the descriptor mechanism is a class level mechanism because it applies to all of the instances of customer. Okay, so that's why you instantiate the descriptor in the class. You don't want to be instantiating non-blank descriptors for every customer. You know, if you have 1 million customers, you don't want to have 1 million instances of non-blank and 1 million instances of this other non-blank. Actually, you would have 2 million instances. If you have 1 million instances, if we implement it like you described, what would happen would be that if you have 1 million customers, you have 2 million instances of this non-blank stuff. And the second thing is, it wouldn't work really because in order for the descriptor to do its magic, it has to be a class attribute. It doesn't work as an instance attribute. Okay? But what happens is, when you do this, immediately in the init, where I'm actually assigning the values, this is already operating. This attribution here, this assignment here, goes through the set method of the descriptor. So this code is already protected by the business rule that is implemented here, as is any other code that takes an instance of customer and tries to assign to .name. Okay? So this is a very important point, that in the init here, we are already taking advantage of this functionality. So this is already guaranteeing that if I pass a blank email, this will give an error. All right? So going back to this description of this code, what happens is we have the non-blank name. So this creates the non-blank instance with a storage name of name. And this creates the other non-blank instance with the storage name of email. Now, this code is not very interesting, except that underneath the cover it's using that. So let's explain that. What happens when you construct an instance of this guy, like for instance, when you do this, customer, you pass Buster and 99, like here. Buster is the name of the customer, 99 is what I'm giving as the email, okay? So this gives me an error. How does that work? What happens is, with this assignment here, self-name equals name, the set method is invoked. The set method gets actually this implicit parameter, which is also in all instance method itself, but there's this other parameter called instance. And what am I talking about? Isn't self the instance? What's the difference between this instance and that instance? What do you think? Yes, there are instances of the different classes. Self is the instance of the non-blank class, which is a descriptor, one of those red guys. And instance is one of those blue guys. It's an instance of customer. All right? So it makes sense that the set gets this other instance, because usually it's going to manipulate that other instance. It's going to store information in that instance, right? And then it gets the value, which in this case is name here, or whatever this string was passed here is, in this example, is the string Buster, right? So it gets a reference to a specific instance of customer and the value, which is the string Buster, right? So what it does is it checks whether this value is an instance of string. If it is, if it's not, it raises an error. It also checks whether it's empty. If it's empty, it raises an error. And if all goes well, which is the case in the first assignment here, because Buster is a valid name, what it does is it takes the instance object, which it got as the second argument, and almost every Python object has a dict attribute that is actually a dictionary that contains its attributes, a mapping of the names of its attributes and the attributes. And the reason why I said almost is because there's a special feature in Python called slots. This is an optimization feature that represents the values of the fields in a class using a tuple instead of a dictionary. So it saves space. But this is an optimization, and it breaks some of the behaviors. So it's really not recommended as something that you should do all the time. It's an optimization that you should do when you actually do have a memory problem because you're handling 1 billion instances of something, okay? So, but that's the only exception. If you don't have a slots attribute in the class, then the instances have a dict. And if I use that storage name I use the storage name as the key. I could put any key, but I'm using the storage name that I got in this constructor here, and I set the value there, right? And because this is a low-level mechanism, it does not trigger the calling dunder set again. Okay, if I try to do instance dot name, or if I try to actually access the name attribute directly, or the storage name attribute directly, I would have an infinite recursion. So the reason why we have to do this through the dict is to avoid triggering the whole mechanism that was triggered when I did this. Okay, I don't want to call dunder set again as a consequence of this manipulation. So that's why you do this low-level thing of touching the dict. Okay. The second time I try to do that, because the value is 99, it fails this test, and an exception is raised. Okay. And what happens when somebody tries to retrieve one of those values, like for instance, customer.name? What happens is, because this descriptor does not implement a dunder set method, a dunder get method, then the usual mechanism is used. And what is the usual mechanism? Python will look in the dict of the instance if there is an attribute with that name. So, does that make sense? So if you call customer.email, it's going to look in the dunder dict of customer if there is the email key, and if there is, it retrieves that. Okay? So basically, when you are using the same name that is the public name of the property that you're implementing as the name for storing it, you don't need to implement the dunder get, because the usual behavior of the dunder get is to get that attribute in the dict. Yes. 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 Exactly. Exactly. Mm-hmm. Yes. Okay. Now the problem is that this is error prone, right? Because in the real world, you may be creating a customer class that has 60 fields, and you're probably going to use copy and paste, and you may forget to change one of these names, and then you're screwed. Because it won't complain, it will just clobber one variable with the other, and you're going to have a mysteriously behaving object that when you assign to the age, it changes the fidelity points or whatever, So this is really bad. It works, but it's error prone. So the problem is that it's not easy to solve this problem, because here's the thing. In languages that have this kind of syntax, this kind of assignment syntax, and that are object-oriented, like Python and Java, and JavaScript even, and Ruby, what happens is the right side of an assignment is executed first. This is a basic fact. Why? Because first you have to have an object so that you can have a reference to it. Okay? And this is actually different from the way C works, evaluates code, right? Because in C, a variable declaration is a space allocation. So that happens, and then some value is put in the space, but not in the in this kind of language, like Python, JavaScript, and Ruby, and even for most variables, reference variables in Java are like that too. What happens is first the object is created, and then there's this binding that happens with this name. And you can actually prove that if you do a test in the command line. You just do y equals and put some invalid expression. If you run that, you're going to get an exception. The y variable is not defined. So that means that the right-hand side was executed first. And because this side is executed first, if I don't pass the name, there is no way this code is going to know what binding is going to happen in the future. Does that make sense? So this is the problem, okay? So one way of solving this problem is to have a class attribute in non-blank that will count the number of instances of non-blank that we are using in your system. And we use the number as part of an identifier to create a storage, to synthesize a storage name. So let's look at the code. In this case, I don't need to pass the name here. But what before was just a parameter that I got in the init here that was the storage name, what I get now, I don't get it now, but I compute it. And how do I compute it? Basically, I get the name of the class, which in this case is non-blank, the name of this class. And I compute a storage name by creating this, by using this format string. Basically, it's the name of the class and the field count. It's missing the rest of the line here, okay? So basically, it's going to create an attribute. It's going to create a name like non-blank underscore 0, one blank underscore 1, non-blank underscore 2, 3, and so on, okay? So the storage name, instead of describing the attribute that is managed by this descriptor, is just a syntactic name. The rest is really no change. The only other change is that I lose some information, right? Here I was able to tell the user that email must be of type string or name must be of type string. Now I don't have this name anymore, and it won't be useful for the user to say non-blank 0 must be this or that. So I just changed to a generic message saying non-blank must be of type string or non-blank must not be empty. Okay? And now I have to implement the dunder get. Why? Because the name where I'm storing the information is not the public name of that property anymore, like it was before. So now I have to implement the dunder get. The dunder get gets an instance as the attribute. And the owner is actually a reference to the class of the instance, but I don't use this here. Okay, so if the instance is none, that means that this attribute lookup is happening on the class. You know, remember when I did dog.pause? So that's looking up the attribute on the class, as opposed to fido.pause, that's looking up the attribute in the instance. So when you're looking at the attribute in the class, the instance becomes none. Okay? So this is the proper behavior in that case. If I don't want to override it, I just return self, which is the descriptor, right? The descriptor is an attribute that's hanging on the class. So this allows somebody to inspect the descriptor when you access through the class. When you access through the instance, you have the getter machinery involved, but when you access a descriptor to the class, maybe you want to inspect the descriptor, and that's why you return self. You return the descriptor itself. In the other case, I use the built-in function getAtter to obtain from the instance the whatever is in that storage name. I don't need to use dunder dict here. I can use getAtter. So now I don't have a duplication, but the problem is that it's hard to debug, because if you inspect an instance, for instance, I am inspecting the dict of Jack. What I get is non-blank 0 is John Robinson, non-blank 1 is Jack at rob.org. So you lose the information of what the fields are. So this works, but it's a pain to debug if you need to debug it, right? Because if, the names of the attributes will be meaningless like that. Yeah, okay. So the last step, and here's where all of the content comes together, because if I can control the creation of the class, then I can solve that problem in a better way. What is the problem? The problem is that I want to be able to know exactly the names of the attributes where those descriptors are going to be bound to, okay? So if I have some way of controlling the creation of this class, of observing the creation of this class, or interfering with the creation of the class, I can do that. And the easiest way to do that is using class decorator, okay? So again, the doc tests go back to using descriptive names for the fields, okay? Instead of non-blank is the name of the field. And this is how it works. So the decorator, name it fields, a decorator applied to a class, okay? So how does this work? Basically, Python will build the object that describes the class and pass that as a parameter to this function. And this function can do whatever it likes to that object and return a class. So it's the same idea of the function decorator applied to a class now, right? Usually what happens is not that a whole new class is created, but it's more common that the class itself is returned after being manipulated in some way, okay? And this is the manipulation that's going on. First of all, take a look at what happened to the descriptor is it's much simpler now, because it doesn't need the field count anymore. It just has the setter. The setter assumes that there is a storage name attribute in the descriptor, but there is no init that creates it. And there's no need for the dunder get anymore, because the storage name will be the public name of that property, okay? And the whole magic happens in this code, which is not very difficult to understand. So the decorator gets the class as an argument, and then it iterates over the items in the class dictionary. What is the class dictionary? So the class dictionary is where the class attributes are stored. How many items are in this class dictionary? 4. This item, which is an instance of non-blank, this other item, which is an instance of non-blank, this item, which is a function, and this other item, which is a function. So you have 4 objects. So this loop goes around 4 times, and each time it checks whether the attribute that I'm looking at is an instance of non-blank. If it is an instance of non-blank, because now I'm looking at the dictionary of this class, I have the name, which is this name and email, and then the init and full name and full email. The name of the attribute in the class, right? And this is what this is what I needed from the start. Now I have it. So I just set the storage name attribute of that attribute as that name, right? So what happens is when this class is defined, the class decorator really doesn't change anything in the class, but it goes into the different descriptors that are used in the class and configures them correctly. Right? And yeah. Okay, so this is another homework because we only have 5 minutes now. Okay, but this is an interesting homework that I want to talk about really, because I have to explain something. You don't really code decorators like I did in the same module where you're going to use them. This is just for didactic purposes, to have only a single source code that we can look at, because it doesn't make sense to do it this way. What happens all of the time when you create descriptors and decorators, really, is that you create them in certain modules that you're going to use all over your program. Does that make sense? And so what you want really is to create another module so that this machinery is not exposed to whoever is using your descriptor. Right? The person doesn't need to see this code or that code. What the person needs to know is use this decorator in the class, and then you can use those descriptors there. Right? So this is the solution, right? From module import, for module 5b import named fields and unblank, and I just use this stuff here. So now you're back to this illusion of simplicity that Django provides. Right? My code is really simple. Yay. But don't forget that but in Django they use another mechanism, right? Because they use, this class has to inherit from another class. And what they are using there behind the scenes is another mechanism called meta classes, but it's more complicated than what I explained and more powerful. But I really advise you to use class decorators instead of meta classes whenever the class decorator solves the problem, because they are easier to think about. And so, yeah, anyway, this is how I end. If you can replace the decorator with a meta class, this would be a more advanced solution, and oh my God. This is really weird, because the way meta classes work is, a meta class is a class, like type in Python is a meta class that creates classes, right? If classes are objects, then they must be created by other classes, and those other classes are called meta classes. And Python comes with a very popular meta class called type. And this is really weird, because when you insert a meta class, suddenly you have this other relationship here. See, the customer inherits from object, but is an instance of model meta. Oh my God, this is complicated, okay? But this is basically what happens in the end. But the important thing is, for the end user, and this is what Django does, it's all encapsulated in a package. The end user just knows that, oh, I have a customer, and there's this field and this other field, and you don't know that all of that is going on in the background. Yes, yeah, exactly. So one way of making all of this more robust is to include diagnostic errors, for instance. Because the way I implemented this will only work if this decorator is applied. But it will, in this case, it will just blow up with an unhelpful explanation. But probably I could take care of that and say, before blowing up, I could say you should have applied the named field decorator to the class where this descriptor is being used. Something like that, Yeah. It was really never my intention to talk about meta classes today. I forgot to delete these slides because I knew we were not going to have time, but there is an example that you can read later, okay, of implementing the same thing that we did with the decorator, the class decorator, with a meta class. And but the class decorator is easier to create and understand, but the meta class is more powerful and easier to hide away into a module, so that the user doesn't know what's going on. So like what I'm saying is, like in Django, when you inherit from model, you just think you're getting all that magic from inheritance, but it's not only inheritance. It's also a meta class that changes the way the attributes work in the system. So, but you have this comfortable illusion of, oh, I'm inheriting all this magic from model. Okay. Yeah. So this is basically it. I have. Let me see. Yeah. Well. Okay. So I have slides in the other presentation that are reference slides that I wanted to show you, but no, they're not here. Yeah, I don't know. The mystery of the slides. Anyway, when I learned this stuff, I want to tell you, because first of all, most of this stuff I learned actually reading the Python in a Nutshell book by Alex Martelli, an older edition, and a new edition of this book just came out. The way that they explain, now there's 3 authors, is Alex Martelli and Anna Ravenscroft and Steve Holden are the authors of the new version of the Python in a Nutshell book. They really understand this stuff really well, and Alex, who was the only author of the previous edition, already explained really well in the other edition, so I am trying to get to the end here. Already explained very well in the other edition this whole mechanism of the dynamic attribute lookup and what the descriptors do and so on, so that's a very good reference. Another very good reference is the Python Cookbook by David Beasley, and also his other book called the Python Essential Reference, also goes very, very deeply into this subject. And my presentation here was really extracted from my book, Fluent Python. Part 6 of the book is called Metaprogramming. And this is like a summary of some of those chapters in part 6 of my book. And yes, that's where I learned this stuff. And yeah. Any questions? Suggestions? If you want to send feedback, this is my email. I would love to get feedback. I would also love that you evaluated the talk in whatever mechanism they have. I don't know the URL. There was this other URL here, but I don't know if it's the same. SurveyMonkey, no, it's not the same, because it says SurveyMonkey.r/PyCon 230. PyCon 230 maybe was the code for that other tutorial in the morning. I'm sorry I don't have one of these. Anyway, let's try and find out. If you send me a question, where do I evaluate your thing? I will try and I'm going to ask the organizers and give you the URL. It has? Yes. Yeah. Yes, yeah, exactly. We need to find out what goes instead of the 230 at the end of that URL. Yeah. yeah, it's the same. Okay, yeah. Yeah, maybe. All right, folks. So the URL that you should go to is surveymonkey.com. I'm going to write it here. surveymonkey.com/r/PyCon 230. Yes. And it's actually HTTPS, but yes. So here's the thing. Some people complain that Python became too complicated. I actually have a very good friend that became a huge fan of Go and Go evangelist, and he says that one of the reasons was that Python became too complicated. And I think he's right that Python is a more complicated language than Go. However, Python is much easier for beginners. Python has more concepts in the long run, but for beginners it's easier. And the reason is because we have these nice things. Like for instance, one thing that Go also doesn't have and that Python has is operator overloading. Now, operator overloading in C++ was abused by lots of people, supposedly. And so, for instance, the designers of Java decided not to have it. The designers of Go decided not to have it. People abuse this feature. Yes, people abuse. But when people use it well, what you get is NumPy. And when you have NumPy, you have all of this importance that Python has today in the analytics field. Because it simply is much easier to do math in a language that has operator overloading than in a language that doesn't have operator overloading. Your formulas look really ugly when you don't have operator overloading. You can't multiply a matrix by another by saying A times X, A times B or whatever. So, and I think this is also both features that I talked about today are features that a user can use without really understanding everything that's going on. But oh, you want to do a view in this framework, you use this decorator and it's going to become a view, okay? You don't need to understand what's going on in the background. It will save you boilerplate and it will make your code readable, even if you don't understand exactly what's going on behind the scenes. So I think we have to consider this. And also, I think Python is really, really well designed, and one of the ways in which this is demonstrated, and it's really interesting, is because the features are not gratuitous. They are always well thought out, and they have multiple reasons to exist, usually. So for instance, the descriptor mechanism, although it's very interesting for end users like us to do stuff like the kind of thing that we are doing, it's also used by the language itself to do one critical thing, which is transforming functions into methods. Think about that. How is it that if you have a function f in a class, def f inside the class, and you access it through the class, you have to pass the self parameter explicitly, but if you invoke it through an instance, you don't have to pass the self. If you inspect those two objects, what you will see is that one is just a function, and the other is a bound method. And what is a bound method, really? The thing is, every function in Python is a descriptor, folks. This is awesome. Every function in Python has a get attribute. So when you just place a function inside a class, it's a descriptor. It behaves as a descriptor. And when you invoke it in that context, through an instance or through a class, it will give you either a bound method or an unbound method. And so I think this is really neat, that the mechanism was, I don't know what was the original intent of this mechanism. It's now leveraged by lots of different frameworks to do fun stuff like Django does, but it's also used by the language itself to unify the concept of functions and methods and make functions behave as methods when they are inside classes. Right? Who thought of that? Every function is a descriptor, folks. Right? Yeah, I think this is really well designed, this whole Python thing. That's why I love to teach it. Okay, any questions? All right, folks, so thank you very much for attending. I hope this was fun for you.